Would you dare to question the validity of almost all mathematics? This is the story of someone who did. It's the story of the disbeliever. Some things sound far too absurd to be true, and yet highly educated people believe this stuff. First up is the idea that 0.9 recurring can equal 1. Almost all mathematicians believe it does equal 1, and that we can prove it using many different arguments. But to many people, these arguments sound like pure gobbledygook. So let's fly in the face of the experts and argue against 0.9 recurring equals 1. Let's be a disbeliever. Mathematicians will spurt out some clever sounding argument. But when we unravel what they are really saying, it sounds more like a religion than down-to-earth logic. It means by the definitions and rules in their holy scriptures that 0.9 recurring equals 1. It is the same as arguing that Darwin was wrong, because God created man, and this can be proven given what's written in holy scriptures. For 0.9 recurring equals 1, they claim that real-world evidence is irrelevant. The only thing that matters to them is what's written in their mathematical scriptures. They will claim that mathematics doesn't depend upon the real world. For them, a system of mathematics depends upon axioms, definitions, and rules of logic, all of which are as fictitious as a fairy tale. From the viewpoint of a disbeliever, this sounds like madness. If the basis of mathematics is a bunch of made-up fairy tales, then the basis of mathematics is obviously flawed. If we are allowed to make up definitions and rules, then we can prove anything we want to. This approach makes a complete mockery of mathematics, and even if we accepted this approach, then the chosen logic behind 0.9 recurring equals 1 is so bad, it's like choosing logic to support the statement that evolution is wrong. Mathematicians claim that consistency is all that matters, not any connection with physical reality, so for them it's fine to believe in fairies and ghosts, as long as everything we say about them is consistent. But that's not good enough for a disbeliever. We need physical proof that these things exist. Otherwise, we claim it's perfectly reasonable for us to disbelieve mathematician statements about fairies and ghosts. And for exactly the same reason, we claim it's perfectly reasonable to disbelieve their statements about 0.9 recurring being equal to 1. It's fine to theorise about written fairy stories or image ghosting on a TV or computer screen, because these things can exist in our shared physical reality. Then any theories about these things can be tested using real-world physics. In the same way that counting numbers can relate to physical objects, surely there should be a way for 0.9 recurring to relate to the real world. In summary, the disbelievers' three main arguments are that non-physical objects do not exist, that we can't conceive of the infinite, and that it can't be a valid approach to simply reject any argument we don't like. As disbelievers, we will use real-world logic, and that logic is as good as logic can get. But we'll still struggle to convince the mathematicians, because they will completely reject our logic based on real-world physics. They believe infinity is a valid concept. They believe that the only rules that matter are the ones that they have made up. And they insist that we must accept their strange system of weird rules, and they will completely refuse to even contemplate that the whole basis of their so-called real number system might be flawed. They could define all the terms and rules for a ghost belief system. They could do this in a way that makes the phrase, "ghosts go through walls," appear to be a valid statement according to their belief system. But this just goes to show how absurd the approach is, because by that method we can literally prove anything we want to. So how can it be valid for them to claim 0.9 recurring equals 1, when they've simply made up all the rules. As disbelievers, our core argument is that only real-world logic can be shown to be valid, and we think that validity is what really matters, not consistency. By our logic, 0.9 recurring can't have a constant value, but it can have a valid real-world meaning, as being the description of a process. The mathematicians say we must accept their definitions and their rules, but we don't accept them. This is a really important part of our argument that they just don't get. Their position is like a belief in ghosts. We are discussing the validity of 0.9 recurring equals 1, and validity doesn't mean consistent given some made-up rules. The only way to prove that something is valid is through empirical evidence in our shared physical reality. Intuitively, does 0.9 recurring equal 1? For a disbeliever, intuitively, 0.9 recurring must be process-related. But for most mathematicians, 0.9 recurring equals 1 has an intuitive explanation that forms the basis of what's called the epsilon delta definition of a limit. If you think 0.9 recurring can't possibly equal 1, then the mathematicians have good and bad news for you. The good news is that they will accept an argument for 0.9 recurring does not equal 1, but only if you've redefined 0.9 recurring to be something other than a real number, and you've used your own non-standard rules of logic. The bad news, they will tell you, is that by default, 0.9 recurring is a real number, and if you use the accepted rules of real analysis, then it is a provable fact that 0.9 recurring equals 1. If you are not a mathematician, then all of this might sound very confusing and very strange. Surely it either equals 1 or it doesn't. But now we're being told that the statement can have different meanings in different mathematical systems. That sounds very weird. What's going on? Before we discover the mathematician's intuitive explanation, let's consider the intuition of a disbeliever. A disbeliever's first thought is that surely something as fundamental as a number should have a tangible meaning. Take the fraction 1/3 for example. We call it a number, but isn't it really two numbers with a line between them? It has a tangible meaning in that we know it means 1/3 of something, such as 1/3 of a cake for example. But then what tangible meaning can 0.9 recurring have? It appears to go on endlessly. And surely there can't be an actual infinity of digits, because that would be absurd. If we abandon the idea that 0.9 recurring is a single value, and we think of it as a sequence of values, then we can give it a tangible meaning that we can relate to the real world. The sequence could represent values that could be produced from a set of instructions, otherwise known as an algorithm, such as one for travelling distances between positions A and B. Step 1 tells us to travel 9/10 of the remaining distance, so from the start this will get us to position 0.9. Step 2 simply tells us to go back to step 1. This time, 9/10 of the remaining distance will take us to the position 0.99. And if we keep following the algorithm, we will be following the 0.9 recurring sequence of values. And so 0.9 recurring is short for the sequence 0.9, 0.99, 0.999, and so on, which are values that could be produced from an associated algorithm. Each attempt to follow the instructions will be a process, and each attempt to follow the instructions must come to an end at some point, so everything here is finite. So there's no infinite process here, just a finite set of instructions. This interpretation of 0.9 recurring is completely finite. We can construct lots of different sequences, but only a few of them will map neatly onto the place value system of base 10 decimals. Each term in the sequence 0.9, 0.99 and so on is the nth sum of the corresponding series. And since it maps neatly to our decimal system, we can write it in a way that looks like a decimal. Mathematicians refer to the nth sum expression as the partial sum expression. Disbelievers might prefer to avoid the phrase partial sum, as it implies that there's a full sum, and for a disbeliever there isn't one. The mathematicians will tell us, no, that's not what 0.9 recurring means at all. It represents an abstract object called a real number. And we can think of real numbers as being points on a number line. Using this number line concept, they claim there's an intuitive way to show 0.9 recurring must equal 1. First, place 0.9 on the number line. And notice that the distance between that point and 1 is 1/10. Next, place 0.99 on the number line. And notice that the distance between that point and 1 is 1/100th. Put 0.999 on the number line, and the distance to 1 is 1,000th. Generalising, the distance from the nth term to 1 will be 1/10 to the power n. So if 0.9 recurring was less than 1, we should be able to find a point that's between 1/10 to the power n and the point 1 for all possible values of n. And since no point exists, it must equal 1. In other words, they are saying that 0.9 recurring must equal 1 because if you give me any point before 1, then I can find an nth sum that's closer to 1 than your point. But this is a cat and mouse argument, and we can easily switch the roles of cat and mouse around by saying, you give me any nth sum, and I can give you a point that's closer to 1 than your nth sum. And since this will work for all possible nth sums, points must exist between 0.9 recurring and 1. So these are two equal and opposite arguments. One implies there can't be any points between them, and the other implies there must be points between them. You might think this shows that 0.9 recurring cannot be any fixed value, and so it must be process related. But the mathematicians want to justify their preconceived notion of so-called real numbers, in which a real number has a fixed place on the number line. So they choose to only accept arguments that fit in with what they want to be true. So they want the first argument to be valid, and the second argument to be invalid. It doesn't matter a jot that these are exactly the same argument just switched around. It doesn't matter that this is an inconsistent approach to logical reasoning. The only thing that matters to them is that they can claim their concept of real numbers is consistent. And if it can be made consistent by rejecting the second argument, then so be it. To a disbeliever, this can't be a valid approach, because any ridiculous notion can be called consistent if we are allowed to reject any argument that shows it to be inconsistent. So the first problem with the mathematician's intuitive explanation is that they reject an equivalent argument. Another huge problem is the whole idea of infinitely small points on an infinitely divisible, infinitely thin number line that goes from -infinity to +infinity. I can imagine a thick line, but when I try to imagine an infinitely thin line, it completely disappears. I don't believe anyone can imagine infinitely small points and infinitely thin lines. I believe those that think they can are wrong. They can't prove that they can conceive of the infinite. It's a matter of belief and faith. And a third major problem is the problem of the last term. Given that all the points in the sequence 0.9, 0.99 and so on are supposedly static points on the number line, then how can there not be a last point? If we approach the number line from the right, then which of these static points will we encounter first? Or, if we think of these points in an ordered infinite set, and we add a number that's bigger than 1 to this set, what number will immediately precede it? We can't just avoid the issue by saying the least upper bound is 1, because 1 is not in the set. Or if we approach 1 from the left, then how can we have passed an infinite amount of these points when we reach the point 1? And how can we not have passed a last point? But the mathematicians will claim there's no problem of a last point, because mathematics has been formalised in such a way that these problems cannot be stated. We are not allowed to ask which of the static points is the last one. We are only allowed to talk about the least upper bound or supremum. In other words, yet again, They have simply decided to dismiss any arguments that would expose a problem with their preconceived ideas about so-called real numbers. So their supposedly intuitive explanation not only requires you to be able to imagine infinitely small points on an infinitely thin line, but it provides no intuitive real-world example, no reason for rejecting the argument that it cannot equal 1, and no intuition on how there cannot be a last point. They'll say 0.9 recurring equals 1 is a statement about real numbers, and so if we want to discuss the validity of this statement, then we must accept all their rules of real analysis, otherwise we're not talking about the same thing. And if we accept all their made-up rules about non-physical abstract objects, we'll have to admit they are right. Almost all mathematicians have faith in their arguments for real numbers, but not quite all of them. A few mathematicians reject infinity, and one mathematics professor has spoken out. He claims that real numbers are at the core of most foundational problems. There is no such thing as the square root of 2. There are no such things as infinite sets. We need to rethink a lot of mathematics. We need to expel infinity. And the statement 0.9 recurring equals 1 should be taken with a large grain of salt. When we examine the timeline for the development of the modern concept of a limit, we find there was a period of over 200 years from the introduction of unending decimals by Simon Stevin in 1594, before several mathematicians devised the limit approach to real numbers. If the limit argument is so intuitive, then why did it take so long to be devised? So who wins the battle for the best intuitive explanation? As disbelievers, we relate mathematics to physical reality, and 0.9 recurring is process-related. Nobody can truly conceptualize infinitely small things. Mathematicians simply reject any troublesome arguments, and they think it's fine to avoid problems by not allowing them to be formally stated. At the end of the day, it doesn't matter what disbelievers think, because the mathematicians decide what the rules are in their abstract world, so if they claim that their intuitive explanation is correct, the rest of us are expected to just accept it. And since people generally like to believe in non-physical things, and that they can conceive of the infinite, the supporters of real numbers will always be viewed as the winners. Let's examine some popular arguments for 0.9 recurring equals 1. Speaking on behalf of disbelievers, real numbers are not intuitive. They rely on the concept of infinity. And any argument against real numbers will simply be declared to be invalid. So now let's examine some other arguments for 0.9 recurring equals 1. Three common arguments are that 1/3 equals 0.3 recurring, so it follows that 1 equals 0.9 recurring. If we subtract 0.9 recurring from 1, we get 0. And finally there's the algebraic proof that 0.9 recurring equals 1. We'll examine each of these arguments in turn. First up, 1 divided by 3. We are indoctrinated at an early age into believing that a division process such as 1 divided by 3 can yield an infinite result. And given that a whole cake can be divided into 3 parts, then 3 times this infinite answer, which is 0.9 recurring, must equal a whole one. But does the division process really produce an infinite result? After getting the first 3, there's a remainder of 1/10 that still needs to be divided by 3, meaning there's a remainder of 1/30. After getting the second 3, there's a remainder of 1/300. After the third 3, a remainder of 1/3000, and so on. And in general, after producing n decimal places, there is a remainder of 1/3 times 10 to the power n. So there will always be a non-zero remainder. The remainder can't go away. But as young children we are duped into believing that an actual infinity of decimal places is theoretically possible, and that this supposedly makes the remainder disappear. This disappearing act can supposedly be demonstrated on the number line. After n decimal places, the distance to 1/3 is 1 over 3 times 10 to the power n. Then if we assume an actual infinity of digits is possible, then no points can exist on the number line between 0.3 recurring and 1/3. If there are no points between them, they must be the same value. But we can flip the argument around and say there is a positive distance between 1/3 and any given number of decimal places, and this holds for all infinitely many of the decimal places. This would appear to show that either 0.3 recurring cannot exist, or if it does, then it can't equal a constant value. This is the same game of cat and mouse that we saw in the intuitive argument for 0.9 recurring equals 1. We have two equal and opposite arguments, one favouring equality and one favouring inequality. Surely if you're going to be consistent in your scheme of logic, then you can't completely disregard one of two equal and opposite arguments, just because it doesn't get you to the answer that you want to get to. But it appears mathematicians can decide what logic to accept and what to reject. This begs the question, how can there be any value in mathematical proof when you're allowed to make up all the axioms and make up the rules of logic in order to prove anything you want to? And the reason they wanted this particular result was to support their notion of real numbers through this theory of convergence. They got away with this approach by allowing one side of the argument to be written down using mathematical notation, and by not letting the other side of the argument be written down in a formal fashion. They could then claim it was an invalid argument. Next we have the argument that if we subtract 0.9 recurring from 1, we get 0. Hence 0.9 recurring must equal 1. But if 0.9 recurring is not a fixed value, and instead it's a sequence, then in order to subtract it from 1, we need to treat 1 as a sequence, and to do arithmetic on sequences or series. The number 1 can be converted to the series 1 plus endless zeros. Then if we subtract the series for 0.9 recurring, we get a new series as the answer. Or we could treat 1 as a sequence, subtract the sequence for 0.9 recurring, and get a new sequence as the answer. Perhaps the best approach is to work with the nth sum expressions. And when we do the subtraction, we get a result of 0 plus 1 over 10 to the power n. Unlike 1 and 0.9 recurring, this result can't be mapped to base 10 place values. This result might describe a sequence of journeys in the real world. The first value in the sequence is 0.1, and so the first journey could be to a position at 1/10 of a certain distance. The next value is 0.01, and so the next journey could be to the position corresponding to 1/100th of the total distance. And so on. You'll never get to 0 by following this sequence, and so the result is clearly not 0. Similarly, we could ask, what is halfway between 0.9 recurring and 1? Again, 0.9 recurring is not a single number, it is a sequence of numbers. And so we need to work with sequences or series or nth sum expressions. Then halfway between them will be a series where the nth sum is 1 minus a half of 1 over 10 to the power n, which is the sequence 0.95, 0.995, 0.9995, and so on, which can also be expressed as a series. But just like the result of 1 minus 0.9 recurring, this result can't be mapped to base 10 place values. Obviously, mathematicians will completely reject all our arguments because we are not working with their so-called real numbers. It's like they've defined that the creation of man must be as described in their holy scriptures, and we are not allowed to believe in evolution because they say we must accept their religious doctrines. Finally, we have the well-known algebraic proof that goes like this. Let x equal 0.9 recurring. So 10x is 9.9 recurring. Then we subtract the first line from the second, giving 9x equals the number 9. And so x must equal 1. Now let's redo this proof, but with 0.9 recurring as a series. We write the same line down again, and note the one-to-one correspondence between the terms of the sequence. Then we multiply the top line by 10. Note that each term of the series gets multiplied by 10, and we keep the one-to-one correspondence with the original terms. Now we do the subtraction, and the resulting series on the right-hand side is 81 over 10 plus 81 over 100, and so on. It is not the number 9. If we wanted to get 9 as in the original proof, we would have to shift the terms, breaking the one-to-one correspondence, and we would have to believe that we can match all of the original terms with all the original terms less one of them. But can we really do this? We could test if this logic is correct if we could find a case where the trailing part cancels out in both scenarios, when we shift the terms and when we don't shift the terms. And this series fits the bill. On the left-hand side we won't shift the terms, and on the right-hand side we will. We'll shift by one place as in the proof. We do the subtractions, and we end up with 0 equals 1, which is a clear contradiction. So this tells us that we can't match the original terms with one less than the original terms. And so the original proof is flawed, and it doesn't prove that 0.9 recurring equals 1. Yet again, the mathematicians will claim we're not following their rules. But we used the series 1 plus 1 plus 1, etc. to test the logic of matching all the original terms with one less than all the original terms in a subtraction. The only thing that's relevant to the cancelling out is that the series is endless. But the mathematicians will claim that we can't test the logic with a divergent series. And we still can't understand why. All of these series are simple geometric series, so in that sense they all have the same structure. They just have different first terms and common ratios. And so we stand by our argument that the shift and subtract logic is completely invalid. In fact, it could be argued that every converging series contains diverging series hidden within them. If we allow regrouping of terms, then even a converging series like 0.3 recurring can easily be converted into 3 series, such as 1 plus 1 plus 1 and so on, minus 1 minus 1 minus 1 and so on, and the original series itself. Then we can line up the terms at different offsets, making the whole thing tend towards different values, such as 1 1/3 or 2 1/3 and so on. If sequences and series have real-world meanings, then this would come as no surprise, because obviously the rearrangement of terms will change the meaning of a series or sequence. The mathematicians will say that 3/10 plus 3/100 and so on is an absolutely convergent series, and we would only be able to make it converge to different values if it was conditionally convergent, because then the Riemann rearrangement theorem would apply. They're effectively saying that it's fine to rearrange terms as long as it can't be viewed as changing the series from one of their categorizations to another one of their categorizations. In fact, rearrangement can even make a series diverge. So surely we can't claim that different series are fundamentally different kinds of objects just by placing them into different classifications, especially when it's so easy to drift across these made-up classifications by simply rearranging the terms. But we are not allowed to question the mathematicians' rules. And anyway, these written symbols only represent real numbers, and real numbers themselves are the true fundamental objects, not their written representations. So 1 and 0.9 recurring just happen to represent the same real number. Fundamentally, a real number is an equivalence class of Cauchy sequences of rational numbers, which means it's some weird abstract structure that's an infinite set containing infinitely many sequences, each of which contains infinitely many terms. What could be easier to understand or to conceive of in the mind than that? So who wins the battle over the common arguments? Does physical reality-based logic win the day? Does it make sense to say the division process can't do an actual infinity of stages? Is it fair to reject a logical argument by not allowing it to be written down? Should we be forced to accept the rules of real analysis? Do the convoluted classifications and rules concerning the rearrangement of terms sound like they were contrived just to allow mathematicians to reject any arguments against real numbers? At the end of the day, it doesn't matter what we think, because the mathematicians decide and dictate the rules. And sadly, people generally like to believe in non-physical things and that they can conceive of the infinite, and so the supporters of real numbers will again be seen as the winners. To understand how infinity came to be included in mathematics, we need to appreciate the history of infinity in ancient Greece. Our story of infinity in ancient Greece stretches from Zeno's paradoxes through to Euclid's Elements. For a disbeliever who totally rejects infinity, the ancient Greek hero should be Democritus for his real-world based arguments against the concept of infinity. Zeno was trying to make the point that motion can't happen. He devised several philosophical arguments to show that continuous motion is nothing but an illusion. Many of his paradoxes showed that if both time and motion are continuous, it leads to contradiction. And many of his paradoxes are equivalent to considering a person's journey from A to B as consisting of infinitely many smaller journeys. For example, first they must have travelled half the distance, then half the remaining distance again, and if they keep going half the remaining distance, they would never be able to reach point B. We could even relate this scenario to 0.9 recurring by making the first journey to be 9/10 of the remaining distance to point B. The next journey is again 9/10 of the remaining distance. And so on, showing that this process can never reach 1. Zeno argued that we obviously can't do an infinite amount of journeys, and that this showed the notion of movement must be wrong. Zeno also devised a paradox about an arrow in flight to address a scenario where motion is continuous, but where time consists of instants. If the arrow's movement consists of it being in different positions at different instants of time, then the arrow is not really moving because no time elapses in these instants of time. So this claim that motion is impossible is based on the idea that motion is continuous by definition. So what Zeno was really doing was showing that continuous motion was impossible, where strong emphasis should be placed on the word continuous. In summary, Zeno's argument was this: motion is continuous, continuous motion leads to absurdity, therefore motion is not possible. But another Greek philosopher, Democritus, interpreted Zeno's paradoxes as follows: continuous motion leads to absurdity. We know motion is possible. Therefore the problem is with continuous. And so motion must occur but as a series of smallest units of time and smallest units of distance, or what we might now call a series of Planck times and Planck lengths. Effectively, Democritus provided a solution to Zeno's paradoxes. All we need to do is accept that infinite divisibility is a flawed concept. Democritus believed that if nothing could be continuous, then everything must consist of a finite number of indivisible parts, which the ancient Greeks called atoms. and this belief was called atomism. The wider implication is that everything must consist of smallest parts, including any movement, regardless of whether it's real or imagined, has to consist of a series of parts just like the frames of a video or film. Time must consist of a series of smallest parts. There must be smallest parts of matter. Space itself must be granular. The same goes for length. Any real or imagined geometric shapes. And anything you can think of, even if that thing is supposed to be continuous. It's very difficult to imagine empty space as consisting of indivisible parts, because we naturally imagine there's a measurable distance between them. But the distance between two parts of space must be measured in terms of parts of space. So the measurement could be the smallest number of spaces we can travel through to get from one to the other. Many people consider Democritus to be the father of modern science, as he believed in acquiring knowledge from studying the natural world, and the study of things in the natural world is called physics. On the other side of the fence we have Plato, who completely disagreed with Democritus. He believed we acquire knowledge from a realm beyond the natural world, and the study of otherworldly things is called metaphysics. Like today's mathematicians, Plato accepted that perfect circles and perfect straight lines probably can't exist in physical reality. And like today's mathematicians, Plato believed we could imagine these things, although today people don't even question how a finite brain can supposedly achieve this imagining of the infinite, whereas Plato suggested that we somehow connect to a third realm through what he called the second realm of consciousness. His theory of non-physical forms or ideas became known as Platonism. This kind of belief that non-physical things can somehow exist is called metaphysical belief, because in ancient Greece, metaphysics literally meant over and beyond physics. But can we really imagine perfect forms, or are we deluding ourselves? Can we really imagine perfect shapes whose edges are genuinely continuous and thus infinitely divisible? Or must all lengths be a finite amount of smallest parts or Planck lengths? In ancient times it was undeniable that the gods were perfect, and so we can appreciate why Plato might have come up with his ideas about different realms. The battle about where knowledge comes from became the battle for the foundation of modern-day mathematics. On one side of the fence we had Democritus supporting physical reality. On the other side we had Plato, who preferred a foundation based on the mysticism of metaphysics. Physics is restricted to only things that can or could exist in the real world, whereas metaphysics is not restricted and so can include abstract things that are beautiful and perfect. Physics can't avoid undesirable conclusions like having to reject the infinite, whereas metaphysics can easily accommodate infinity by simply rejecting any argument against it. Democritus didn't promote his ideas as well as Plato did. Plato founded a large academy that was the start of all academia, and to this very day, in the academic subject of mathematics, it is mandatory that you accept a Platonic belief in abstract objects, and that you can conceive of the infinite. And so Plato clearly won the battle. The ancient Greeks were still very wary of infinity, and Aristotle tried to make a distinction between two different kinds of infinity. He described an actual infinity as a completed infinity, and a potential infinity as one that is never completed, but where elements can always be added. This potential infinity was devised in order to avoid the problematic nature of an actual infinity. One criticism of this approach is that in order for a potential infinity to exist, we must first assume that the ability to keep adding will persist forever, where the word forever implies an actual infinity. And so this concept of a potential infinity is just a slippery way of disguising an actual infinity. The basis of mathematics was firmly established by Euclid in his publication called Euclid's Elements. And even though Euclid didn't like infinity, he still defined a point in terms that meant it was infinitely small, and he defined a line in a way that meant it was infinitely thin. At least the ancient Greeks tried to define these fundamental concepts. Nowadays, we avoid the problematic nature of defining these things by calling them primitive notions. Instead of admitting that these things are unimaginable and don't make any sense, we pretend they are so primitive that we all understand them, and that no definition is necessary. And that brings us to the end of our story about infinity in ancient Greece. What exactly is infinity, and does infinity exist? The literal meaning of infinite is not finite. It is also claimed that infinite means endless, but can something that's endless really be not finite? In ancient Greece, Aristotle distinguished between these two meanings by calling one of them actual and the other potential. The claim is that something is potentially infinite if elements can always be added to it. So it appears to capture the infinite property of never ending, whilst avoiding the need to have to do an infinite amount of something. But something can't be potentially infinite if the ability to keep adding might come to an end, and so this endlessness approach requires time as well as the ability to keep adding to be actually infinite. Another example of endlessness is a circular running track. It has no end point, but it can't be described as not finite. Yet another example of endlessness is when we get into an endless loop when following a set of instructions. When the execution of a computer program does this, it is called an infinite loop. But we can't go around that loop a not finite amount of times. The instructions are entirely finite, and so is every attempt to follow them. The ancient Greek philosopher Democritus argued that there couldn't be infinitely many of anything, and that everything must consist of a finite number of indivisible parts, which they called atoms. But it's hard to imagine how some things cannot be infinite, like the universe. If the universe comes to an end, then what's beyond the end? And how can time not be infinite? At first, these examples appear to support the concept of infinity, but we need to examine these things further. Take the problem of what's beyond the end of the universe. If matter is physical material, and what we call empty space is also physical material, being made up of lots of smallest parts of space, then we can say the whole universe consists of physical material. It follows that outside of the universe there is no space, no distance, no anything. Therefore there is no such thing as beyond the extremities of our universe. There's not even a place that we can call outside the universe, because of the complete absence of all properties such as distance or volume. This logic has to be considered a bit dubious for two reasons. There is nothing in the real world that we can point to as being an example of this phenomenon, and so in that sense it is a metaphysical argument. And how exactly can there be an absence of all properties outside the universe? The very idea sounds absurd. So perhaps the idea that the universe is infinite is less absurd than it being finite. But we know the distance between any 2 points in the universe must be finite. And if all distances between any 2 parts of the universe are finite, then there can't be an infinite distance within the universe. It would then seem absurd to claim the universe is infinite. But we could ignore this and claim that an infinite distance can contain only finite distances. This is analogous to the argument that an infinite set of counting numbers can exist containing only finite values. So we would be taking our lead from fictitious mathematics. We would be saying that perhaps the real world, the real universe, reflects our made-up mathematical concepts. Again, the logic has to be considered a bit dubious, because there's no real-world example of an infinite thing, let alone one consisting of just finite things. And can we really just ignore the apparent absurdity? Now consider time. Can that not be finite? Well, time is movement. It is what we say takes place when parts of space or matter in the universe change position. If we examine a timeline of time, then time started when movement started in the universe. At any point in time, only a finite amount of time will have transpired. And in the future, maybe all movement will cease and time will come to an end. So we can explain how time can start and end, but we can't explain how a not finite amount of time can ever occur. It is easy to say that something can go on forever, but since we can't explain how it would occur, the claim that time is infinite is highly dubious. Next we have the counting numbers 1, 2, 3 and so on. Given that there's no biggest number, you might think that therefore there must be infinitely many of them. But a robot with a computer for a brain can use counting numbers because numbers are created within the computer as and when required. They don't have their own out-of-computer existence. So why should the human brain handle numbers differently to a robot? Why aren't numbers in-brain objects that are created as and when required? If they are, then with a finite number of brains, there can only ever be a finite amount of numbers. Mathematicians can use the word infinity, but all of mathematics is finite, in that it involves a finite amount of symbols interpreted by a finite amount of brain cells. It is claimed that maths depends on definitions and rules and not on physical reality. So the simple act of walking from one place to another could be modelled mathematically as a supertask consisting of infinitely many smaller journeys. Such an approach might be considered successful for predicting that other journeys could be completed. But this apparent success does not make it a valid approach for modelling reality. Mathematics should be able to accommodate any amount that does exist in the real world, and a lot of people trust their intuition where infinity is concerned. Even the brilliant analyst Bertrand Russell accepted that infinitely many things probably exist in the real world on the basis that a finite amount of things seems unlikely. He said, "We wish to define number in such a way that infinite numbers may be possible. Thus we must be able to speak of the number of terms in an infinite collection." It appears that the majority of our intellectual giants can't stop themselves from believing in the infinite. Perhaps numbers are merely represented within computers and brains, and they really can be said to have their own existence. So let's examine the claim that we can imagine non-physical things like numbers. If we form a mental picture of two cats on the moon, then obviously it doesn't mean that it's true that there are two cats on the moon, but the mental image does exist. It has a physical presence in the chemistry of the brain. And whether we are counting two imagined cats or two real cats, the number 2 forms part of the description, so the number only exists inside the brain. When we see the written symbol for the number 3, we recognise it as representing a numeric quantity. But if all thinking entities such as brains and intelligent machines suddenly stopped working, would the symbol still represent a numeric quantity? It takes a thinking entity to assign meaning to a symbol, and so without any thinking entities, the symbol would just be a meaningless collection of atoms. But what about numbers out there in the universe, such as 8 planets in our solar system, or 6 electrons in a carbon atom? Even without any thinking entities, these numbers would still exist, wouldn't they? But since it requires a thinking entity to define what a numeric count refers to store the concept as data, and to be aware of its meaning, then even though the physical stuff will obviously still exist, the description of that stuff will not exist, and numbers are part of the description. Numbers are created by thinking entities. They are not out there in the universe. It's the same with patterns. Without thinking entities, there are no patterns. Patterns are not out there in the universe. A pattern has no physical existence of its own. This is a very difficult argument to grasp. Patterns are a brain-based interpretation of data. The physical stuff exists, but the identification of patterns is part of our internal data processing. We found that numbers don't exist as symbols, and they don't have their own existence in the natural world. But they do exist within thinking entities. This leads to the following logic concerning how many numbers exist. Since there can only ever be a finite number of thinking entities, and since any thinking entity only has a finite amount of storage, it follows that only a finite amount of numbers can ever exist. But most mathematicians are formalists. They believe mathematics is just a game we play with symbols and rules. They believe these symbols and rules are not subject to physical limitations. They claim this allows for an infinite number of expressions. But we have already seen that even our imagination is physical in nature, and so it is subject to physical limitation. So there can only ever be a finite supply of real or imagined symbols, and if you think otherwise, then you must be deluding yourself. You can't demonstrate or even explain how this limitlessness can occur without first assuming an actual infinity of material or time or both. It would be nice to think that we can keep increasing from a finite quantity to a bigger but still finite quantity forever. But the word forever implies an actual infinity of both time and material. So it is impossible to show how infinitely many symbols can occur without first assuming an actual infinity can occur. Occasionally, a mathematician will rise to the challenge of showing how infinitely many can be achieved within a finite time and with a finite amount of material. Their solution goes something like this. We can construct a computer to set x equals 0 at time 0, then set it to 1 at time a half, 2 at time 3/4, 3 at time 7/8, 4 at time 15/16, and so on. It follows that when time equals 1, the computer will have set x to all infinitely many natural numbers. They will claim that everything here is well defined, and we could protest that they've assumed time is infinitely divisible, or that this is delusional because it can't happen in the real world. But there is an even easier way to defeat this argument. A mathematician's theoretical computer is a Turing machine, which performs one operation at a time. So when time equals 1, we could stop the machine and step back through its instructions to find out the last number it processed. This contradicts the concept of infinitely many, which requires there to be no last number. Of course, the mathematicians could invent a new rule that says we are not allowed to step back through the machine's instructions, and then claim everything is consistent once again. But that would just show how utterly ridiculous mathematics is with its make-believe objects and its made-up rules. And so is there any reason why we should accept the concept of infinity? Well, just because finite things exist, it doesn't follow that non-finite things must exist, even if we think that we can imagine them. Mathematics professor Norman Wildberger claims that non-finite is just a grammatical construction, in the same way that an immovable kitten is just a grammatical construction. And so apart from the desire to believe in weird and strange things, there is no good reason to accept the belief that infinity is a coherent or meaningful concept. Do we really need the concept of infinity in mathematics? If validity in the real world was a foundational requirement of mathematics, then the debate about whether or not to use the concept of infinity would revolve around its validity. For a disbeliever in the current approach to mathematics, this issue of validity is what really matters. A mathematician can prove anything they want to if they're allowed to use non-real-world definitions and use non-real-world logic, and if they can simply reject any argument that would disprove what they want to prove. This disbeliever's argument is that the mathematician's whole approach is absurd, and they need to reinvent mathematics using physics-based axioms and rules. The onus should be on the mathematicians to justify their approach, not on disbelievers to produce a whole new body of work as a replacement for all existing mathematics. But mathematicians think they can dismiss any criticism of their approach on the basis that mathematics appears to work. This is not an acceptable reason to the disbeliever. The theory that the world was flat appeared to work until a better theory came along. And besides, mathematics doesn't work, otherwise it wouldn't have so many problem areas that they like to dismiss by calling them paradoxes or things that are counterintuitive. But instead of addressing the core argument, mathematicians prefer to challenge the disbelievers to reinvent mathematics themselves. This puts the disbelievers at a disadvantage. Instead of talking about the main issue where the disbeliever has a strong case, the focus is switched to the difficult question of how we fix the problem. Now any slight oversight by the disbeliever can be attacked and ridiculed by the mathematicians. Nevertheless, let's give it a try. Our first challenge is pi. If it isn't a real number, then what is it? Well, we can't construct a perfect circle because any shape must consist of a finite number of indivisible parts, like Planck lengths. But we can create instructions that describe a process of continual refinement, where the parts get smaller. So pi cannot be a fixed length, because such a thing cannot exist in the real world. So we might use the word pi to refer to any sequence-generating algorithm with this particular geometric goal. And we still maintain that the onus should not be on us to create a new foundation for mathematics. Of course, we will be told how wrong we are. Modern mathematicians don't even think of pi as being a length. It is an equivalence class of Cauchy sequences, which means it is the abstract structure of an infinite set containing infinitely many sequences, each of which contains infinitely many terms. If we argue that an equivalence class of infinitely many infinitely long sequences is complete and utter nonsense, then we will be accused of not understanding mathematics. The claim is that so-called real numbers can be constructed from the rational numbers, which in turn can be constructed from natural numbers. So first we must accept that all natural numbers exist. Mathematicians can appear slippery where existence is concerned. When they say that all natural numbers exist, it simply means that the concept of infinitely many of them does not lead to any inconsistencies. They'll keep telling us it's all about consistency, and we keep telling them that that makes no sense. To us, it's blatantly obvious that being valid in the real world is what really matters. Otherwise, maths is nothing more than a collection of fairy tales. So they'll keep on using as much mathematical jargon as they can, perhaps in the hope that we'll concede in the face of their superior knowledge. For us, a natural number simply represents or describes a quantity. But they will point us to the Peano axioms for a description of the natural numbers. We can't accept their concept of natural numbers because their jargon has no meaning in the real world. The Peano axioms start with 0 is a natural number. This would be okay if it related to reality, such as being the count of objects in a defined space, but it doesn't. It supposedly has its own mathematical existence. The second axiom says, the successor of any natural number is a natural number. Here, the successor is not constructed, as it would need to be if it related to reality. No. This axiom asserts that all infinitely many successors supposedly already exist. To a disbeliever, this is complete garbage. A later axiom is the axiom of inductance, even though it could be argued that inductance was used in the second axiom. To a disbeliever, inductance is a slippery way to claim that infinitely many of something can somehow occur. A brain is very different to a laptop computer, but it is still a device that processes data. So the obvious thing for a number to be is a piece of data within the brain. Disbelievers can see no reason to believe that numbers are beyond physical reality and that we can somehow imagine these non-existent things. A number forms part of our description of something, such as a length, a weight, an amount of imagined cats on the moon, and so on. Other things called numbers, such as signed values, fractions, complex numbers, sequences like 0.9 recurring, and so on, are composite data items. They contain numbers along with symbols that mean other things. Also, since algorithms should obey real-world logic, then we would only ever encounter a divide by zero problem if an algorithm is constructed wrongly. So if we approach the subject correctly, we should never encounter a divide by zero problem. If numbers exist in brains as the quantity part of descriptions, then it would be a mistake to believe their existence is somehow dependent on consistency, or that we can say infinitely many of them exist. But mathematicians won't listen to such ramblings, as they want to use their formal symbolic language which was designed to convey their strange abstract ideas. They'll think we must be claiming that negative numbers can't exist. Otherwise, how do we explain how -1 apple could exist in the real world? The answer is easy. Just as numbers describe physical quantities, other mathematical symbols, including the negative sign, must also describe physical objects or actions. Once we give the negative sign a meaning for this particular context involving apples, then -1 apple will have a meaning in our shared physical reality. A plus or minus sign can be used to represent binary states in the real world, like forwards and backwards, financial credit and debt, and so on. Once we realize that a sign represents a particular real-world state, it becomes obvious that we could have more signs to represent more states, such as 6 perpendicular directions. then finding a square root of -1 suddenly has a real-world meaning. With an understanding that these signs relate to multidirectional movement, we should be able to find other scenarios for which working with these signs would be beneficial. This makes a lot more sense than having a mysterious imaginary square root of 1 called I, where we have to use inspired guesswork to find suitable applications for it. We can easily say as n increases instead of as n tends towards infinity, and so there is no reason to pretend that we are working with infinity. In differential calculus, we calculate a slope by supposedly narrowing down to an infinitely small point on an infinitely thin line. How can anyone not see how absurd this is? In integral calculus, the area under a supposedly infinitely thin line is thought of as consisting of infinitely many rectangles that are all infinitely thin. The infinitely thin, infinitely many small areas of these rectangles can supposedly add up to a non-zero area. If this isn't absurd, then nothing is. Surely we need to rework calculus to be based on smallest parts. We need to start from the very beginning by defining exactly what the subject of mathematics is all about. We have the crazy situation at the moment where there's no generally accepted definition for mathematics. One attempted definition is that mathematics is the set of all objectively verifiable chains of reasoning possible on a Turing machine. But everything can supposedly be simulated by a Turing machine, and so to avoid endless recursion, mathematics would need to be a subset of algorithms and computing, rather than the other way round. Mathematicians would detest the idea that mathematics should be relegated to being just a subset of engineering, but perhaps that's the way it should be. In the reinvention of mathematics, it might make sense to call it logical reasoning concerning quantities, and for it to be a subset of algorithms and computing. And if algorithms can encapsulate all of mathematics, then they can't be a subset of mathematics. Most mathematicians won't accept that the concept of infinity is absurd. They embrace it, and they even believe that there are different sizes of infinity. They claim that Cantor's diagonal argument proves that the infinity of the natural numbers is smaller than that of the real numbers. But again, it looks like another case of rejecting any arguments that go against what they want to prove. To demonstrate the flaws in Cantor's approach, consider the argument that the infinity of the whole numbers is the same size of that of the even numbers. It sounds absurd to claim that there are as many even numbers as there are whole numbers. Even so, by Cantor's logic, we can supposedly prove this by matching up the numbers in the two lists. We match the even numbers 2, 4, 6 and so on with the whole numbers 1, 2, 3 and so on. After processing up to number 6, we will have matched all 3 of the even numbers and the first 3 whole numbers, leaving 3 whole numbers not matched. If we continue the matching process, then we might say the number of matched whole numbers tends towards infinity, but so does the number of not matched whole numbers. So it is obviously impossible to match all of the whole numbers. But by Cantor's logic, we can simply ignore the not matched problem and just assume that the two lists somehow exist in their entirety with all values in both lists inexplicably completely matched. This bizarre and totally inconceivable state of affairs is supposed to prove to us that there are just as many even numbers as there are whole numbers. Mathematicians choose to accept the mind-bending argument that all values can mysteriously match up, rather than the more straightforward argument that they obviously can't. and as we have already seen, mathematicians can choose to believe whatever argument they want to, and whatever they choose to believe will be declared to be mathematically correct. Next we'll consider Cantor's diagonal argument. To show how a diagonal argument works, consider a list of just 3 whole numbers. The diagonal argument provides a method for finding a value that is not already in the list. First we go down a diagonal and use the digits to form a new value. For our units column, we will take the units digit from the first number. Then we get our tens digit from the next number, and so on. We can assume as many leading zeros as we need. It doesn't matter if the new value is already in the list, because the next step is to change each digit in the new number. We could change any 0 to 1 and change any digit that's not a 0 to be a 0. This method of changing each digit in a diagonal will always generate a number not already in the list for any sized list. But what if we could have an infinite list containing all the natural numbers? Would we be able to construct a number that is not already in the set of all natural numbers? Well, supposedly we could apply the diagonal argument, but our result would be a different type of number. It wouldn't be a natural number because it would have infinitely many digits. To a disbeliever, the concept of infinitely many leading digits is as absurd as infinitely many trailing digits, or infinitely many decimal places, in that it forms an obvious contradiction, because all digits are a finite number of decimal places from the units column, and the representation consists solely of these finite distances. Now consider a list of the numbers 0.0 to 0.9. This list is restricted to non-negative numbers less than 1 with 1 decimal place. And so for this specified type of number, 10 unique values would make it a full list. In order to go down a diagonal, we would have to use leading zeros, trailing zeros, or both. And the result would not be of the same type as the numbers in the list. As with the previous example of the full list of natural numbers, the diagonal argument result is not of the right type to fit in the list or set. Indeed, it is always the case that the diagonal argument produces a result of a different type when applied to a full set of any given number type. Note that as we changed this example to allow more decimal places, such as 2 decimal places, then 3 decimal places, and so on, the size of the diagonal result grows exponentially. So it is easy to appreciate why the diagonal result for a full list will always need to contain far more digits than any number in the list. But now let's assume that all real numbers from 0 up to but not including 1 are listable. If we apply the diagonal argument, should we expect the result to be of the wrong type? Who knows what really happens when we supposedly have infinitely many digits? Perhaps the result will be the wrong type. Perhaps the idea that we can process all of them is problematic. Or perhaps one or more of our assumptions may have been invalid. But if we claim the result will be of the right type, then we can claim to have found a missing value, and hence proof by contradiction that real numbers can't be listed. Then we can convince ourselves that we can conceive of infinities of different sizes, and we can give them different names such as Aleph null and Aleph 1. Mathematicians want infinite decimals to be valid, and so they'll reject any argument against the answer they want to be true. And the answer they want to be true is that we can prove that real numbers can't be listed. For the disbeliever, this highlights the massive shortcomings of proof by contradiction. The biggest problem with proof by contradiction is that it tells you that something in your argument is wrong, but it doesn't say what it is. In the diagonal proof by contradiction, we assumed that the concept of infinitely many is a valid concept. The concept of a real number is a valid concept. A static numeric representation can have infinitely many digits. We can complete the diagonal process on infinitely many digits. The result of the diagonal argument will be the right type. And the list goes on because we assumed many things. Finally, we have the assumption that real numbers between 0 and 1 can be listed. But this last one is what the mathematicians want to claim is what caused the contradiction. So they just claim that all other assumptions are given or assumed to be true. In other words, they simply choose what they want to prove as being the thing that they have proved. This argument is nothing more than complete and utter rubbish. For a disbeliever, there is not one single convincing argument for why we need the concept of infinity in mathematics. For someone who rejects the concept of infinity, it would appear that the mathematics of infinity has corrupted science. Say we discover that 1 in 30 darts thrown at a dartboard bounces out. This figure simply describes a numeric part of the effect. It doesn't tell us the cause of the effect. And that is exactly what mathematics does in science. It describes numeric parts of an effect. It doesn't tell us what caused the effect. Should the scientific approach be to claim the effect of a dart bouncing out of a board is beyond all human comprehension, and so we should just accept the maths? Or would that be the complete opposite of scientific? But this is often the position of our academics. They tell us we should accept there are things beyond our understanding, and if the maths works, then that's all that matters. And if we don't think that the maths provides clarity, then we're probably just not clever enough to get our heads around it. Many scientific theories can supposedly only be described using mathematics. Surely we shouldn't reject something like quantum mechanics just because we don't understand it, should we? Normally, we would concede to the superior knowledge of the academic experts. But perhaps we should fight back for once. Perhaps we shouldn't accept that something is beyond human understanding. Otherwise, we might be tempted to accept the supernatural instead of trying to find a real-world explanation. For us, the maths alone is not enough. We want a proper explanation. And perhaps we should reject quantum mechanics if it really doesn't make any sense. Yes, it might well be true that there are things that are beyond what we perceive to be our physical world. For example, we might all just be intelligent characters in a computer game being played by a greater intelligence. In such a scenario, our physical reality is restricted to things inside the game. We would have no access to the place beyond our reality. We would have no way of knowing that a greater intelligence was influencing or controlling events inside our reality. So yes, it is possible that there might be things that we can never understand. But we should never accept that there are. To do so would allow us to abandon scientific investigation. Once we start to accept that an effect was caused by forces from a realm beyond our world, we will have abandoned the scientific approach in favour of a faith-based belief system. It might be very desirable to believe in things that can never be backed up by empirical evidence, such as there being infinitely many versions of the world, and in many of them everything went right for you. Such theories should not be called scientific, and yet scientists are the ones saying these things. It makes science appear to be a ridiculous and farcical subject. And should the only test of how good a theory be its ability to make good predictions? If we claim that a large invisible space cat makes the sun rise every day, then it might make good predictions, but it's obviously a load of nonsense. In addition to making good predictions, a good theory should provide a greater clarity of understanding, and ideally all aspects of a theory should be supported by empirical evidence. We might invent a theory that says, in order to travel from A to B, we need to complete an infinite number of journeys. But this is not a good theory, because instead of providing a greater clarity of understanding, it creates more confusion with its strange notion of completing an infinite amount of journeys. There's a weird notion that rather than being man-made, mathematics is some mystical language of the universe that we have discovered. Not only that, but it can say things about the natural world that can't be expressed using natural language. This is bizarre. The symbols used in mathematics all have natural language meanings, and so the symbols are just a form of shorthand. The real problem is that some of these natural language meanings have no tangible mapping to physical reality. For example, instead of a mathematical length mapping to a real-world measurable distance, it is claimed to be an infinitely thin extent between two infinitely small points in multidimensional space. We can't sum to infinity in the real world, and there are no physical distances corresponding to pi or the square root of 2. Just finite multiples of Planck lengths. This doesn't mean we should completely abandon pi and the square root of 2. It just means that they can't be static lengths. And so we should treat them as something else, such as process-related functions. Sadly, the world of science has accepted the weird notions of mathematics, even though they make no sense in physical reality. One example of how maths has corrupted science is the slippery notion of multiple spatial dimensions. We are given a story that goes something like this. If we keep zooming in on a flat, apparently two-dimensional object, then eventually we'll see that it's really three-dimensional. We are then expected to believe that by similar logic, even more dimensions might exist that we can't see. But the word dimension traditionally means the measurement of a defined length. So if I measure my foot, leg, waist and chest, then these are 4 dimensions. This concept of dimension has been corrupted by the mathematics of infinity. In mathematics, points in space are infinitely small, and each point can be described by 3 numbers called its x, y and z coordinates. And this is where the idea of 3-dimensional space comes from. But if the real world doesn't consist of infinitely small points, then the whole basis of spatial dimensions is flawed. It means there's not 3 spatial dimensions in physical reality. There's just space. And the zooming in logic that supposedly leads to the possibility of more spatial dimensions that we can't see does not apply. It is highly unlikely that the smallest parts of space are arranged in a nice layout that is easy to model mathematically. But as we don't know how they're arranged, we might as well model them as though they are boxes. Then 3 perpendicular measurements from an origin will uniquely identify any given position. But we could devise a strategy for assigning a unique number to each box. This would allow us to describe any position with just one number. It doesn't matter how many numbers we use to identify a position in space. There's no reason to believe that things might exist in extra spatial dimensions that are beyond our abilities of perception. Yes, we can devise mathematical expressions in which we have more than 3 variables to represent so-called spatial dimensions. But made-up mathematics doesn't tell us about the real world. Maths should be based on physics, rather than physics being based on maths. It is often claimed that only the language of mathematics will allow us to understand various scientific phenomena, such as the weird quantum wave, that is described in terms of probability distribution. But does a mathematical expression really provide an explanation? Newton's equation for calculating the gravitational force between two bodies doesn't provide any explanation about what mechanism produces the force that we call gravity. And in order to understand any mathematical symbol, it has to have a meaning in a natural language. On this basis, there isn't any independent language of mathematics. So why are we trying to describe physical things in terms of maths? And where did the notion of quantum weirdness come from in the first place? Well, it came from the study of small particles, especially the study of the nature of light. The ancient Greek philosopher Democritus argued that everything must consist of smallest parts, even light. Considered the father of modern science, Democritus was trying to explain physical phenomena in terms of simple fundamental concepts. Thomas Young's double-slit experiment in 1801 promoted the idea that light might be a wave. But in 1905, Einstein postulated that light might consist of particles called photons. Then in the mid-1920s, quantum mechanics was devised, in which it was postulated that every quantum entity can act as either a wave or a particle. But other waves in nature can be described as an oscillation of particles in a medium. So our only understanding of a wave is something that is particle-based. Could empty space be a particle-based medium that somehow gives light its wave nature? The medium of empty space was called ether, and in the 17th century Robert Boyle, best known for Boyle's law, proposed that one or two particle-based ethers might help to explain phenomena such as magnetism and gravity. A few years later, in 1687, Isaac Newton described ether as a medium that flows continually downwards towards the Earth's surface, and he talked about an ether density gradient. Could Newton have been right about ether being the cause of gravity? Well, Newton's cradle appears to indicate that energy is conserved when travelling at constant velocity. And since we consider energy and mass to be essentially the same thing, then perhaps mass can move through space at constant velocity without losing energy. In which case, perhaps we only feel the effect of ether when matter or energy is accelerating or decelerating through it. And perhaps parts of space can somehow be randomly created and depleted. Or perhaps matter can transform into space, and vice versa, and maybe these things can pop into and out of existence. And if we suppose that more space tends to be depleted than created where mass is plentiful, then this would cause a steady flow of ether towards the Earth's surface. The ether would speed up as it approaches the Earth's surface because the available volume for it would be reducing. This would result in a constant downward acceleration of ether, which could conceivably create the force we call gravity. A theory of ether, where ether is created where mass is sparse and depleted where mass is plentiful, could be an extra tool that might be useful for explaining other phenomena such as dark energy, dark matter, and possibly other things. Sadly, Newton discarded his theory of ether and used mathematics to describe the effect of gravity without providing a mechanical explanation of what causes gravity. But it was still hypothesized that light was a wave and propagated through an ether. and instead of being a downward force, it was thought that ether would cause a sideways wind-like force on light. Such a sideways force was ruled out by the Michelson-Morley experiment in 1887, and inexplicably many people concluded that ether could not possibly exist. There's an obvious similarity between Einstein's idea that gravity distorts space and Newton's idea of a downward flow of ether forming a density gradient. They both predict that gravity should affect light. If light doesn't propagate through a medium, then how can we explain its wave-like nature? And should we be happy to have only mathematical descriptions for gravity and quantum waves? Instead of just maths, shouldn't we want more tangible theories about the underlying mechanisms behind these effects? If maths alone is insufficient, then we would have to admit that when we talk about something like a quantum wave of probability, we don't really have a clue what we are talking about. Sound propagates through air in spherical waves of pressure. And we have a formula for the amplitude or displacement of particles from their mean position at any given distance. But we know that sound doesn't persist forever, as the mathematical formula suggests. Also, the amplitude doesn't tend towards infinity as we get close to the source, as the mathematical formula suggests. So we can't trust the maths, even though it appears to work in most cases. The maths doesn't properly reflect the finite and granular nature of physical reality. This highlights the problem of claiming that something can only be described by mathematics. The expression A over R tells us that the amplitude decreases as distance increases. But it doesn't explain the physics involved. It doesn't explain why the amplitude decreases. It tells us nothing about the physics of the molecules that cause the effect. Sadly, nowadays, physicists often claim that a particular phenomenon is explained by some mathematical expression. Perhaps it's time for physicists to stop doing this. Even with a theory of parts of space, it is not easy to explain the result of the double-slit experiment. But without any ether, we've got very little to work with. We might, if we were advocates of quantum mechanics, resort to proposing that small particles can somehow choose between acting as a mysterious wave of probability and acting as a particle. And since a single slit appears to result in particle-like nature, we might propose that the particle or wave decision depends on whether or not the result would allow someone to be able to determine which slit it went through. But if a decision is being made, then who or what makes the decision? Are we all subservient to some higher intelligence? It's all very strange. An even weirder inevitability that emerged from quantum theory was that two particles at different physical locations must be able to act as a single entity. These particles were said to be entangled. For several decades, nobody could think of a way to test if entanglement was really happening. Then in 1964, John Bell outlined a test that could be done using the mathematical concept now known as a Bell inequality. And in 1972, the first Bell test was performed. But the large number of missed detections meant that not only was a classical physics explanation possible, but it might have been better at predicting the result. Quantum mechanics doesn't require there to be any missed detections, but a classical physics solution would predict a certain amount of missed detections. They are required in order for a classical physics solution to significantly violate a Bell inequality. But any explanations based on classical physics were sidelined as possible loopholes, and the weirdness of quantum mechanics became widely accepted by physicists. Many Bell test experiments have now been performed, several of which have claimed to be loophole-free, but all of them can easily be contested, and so we still don't have a single definitive experiment that proves beyond all reasonable doubt that spooky quantum entanglement really exists. If we had a definitive experiment, then every aspect of it could be scrutinised in depth. Physical aspects of the experiment could be altered to see what effect it had on the overall outcome. This drilling down into the detail might well indicate a possible classical physics solution. If the advocates of quantum mechanics are right, then they have nothing to fear from such intense scrutiny. They might have nothing to fear, but they would have a lot to lose. Quantum mechanics is currently accepted by mainstream physicists, but this could change if we had a definitive experiment that was debunked. They would much prefer the current situation, where many experiments are described using the terminology of quantum mechanics, in which it is already assumed that a choice is being made about when a wave collapses into particles. This can lead to some very bizarre conclusions. The delayed choice quantum eraser experiment includes a delayed choice of path achieved by changing the apparatus while the photons are in mid-flight. From the resulting patterns on the detection screens, it is deduced that the photons must have somehow reversed their earlier decision as to whether to act as a wave or a particle. How can the decision to pass through a double slit as a wave or a particle be made after it's passed through the double slit? Surely such an explanation is absurd. Wouldn't it make a lot more sense to take into account undetected photons instead of ignoring them, so that a classical physics explanation becomes plausible? But no, the accepted explanation is bewildering. They think that they can really change events that occurred in the past. If something sounds too ridiculous to be true, it probably is. Who is going to believe that scientists can change the past? There's very little for the disbeliever to do here, because the scientists' over-the-top claims are just not believable. This is the Disbeliever's Guide to Quantum Computing. Great claims are often made about the power of quantum computing, but how does a quantum computer work? We'll go through a simple example and get a flavour of what it's all about. Perhaps the simplest example is one that's commonly known as the Deutsch oracle. It has been claimed that this shows how a quantum computer can theoretically outperform a classical computer. Like many of the tasks devised for quantum computers, the Deutsch oracle is of little practical use. And the scenario sounds very obscure and very contrived, but it will serve a purpose if it demonstrates some basic operations of a quantum computer, and particularly if it demonstrates how a quantum algorithm can easily outperform a deterministic classical algorithm. It involves a black box that takes some binary values as inputs and produces either a 0 or a 1 as output for each input combination. The task for the quantum computer is to determine if the black box function is constant or balanced. But what does it mean for a function to be constant or balanced? Well, if we've got a traditional logic gate with 2 binary inputs and 1 binary output, we know the gate is either an AND gate or an OR gate or any one of 16 possible gates. But we don't know which one it is, so the gate is effectively a black box. For the 4 different input combinations of 00, 01, 10 and 11, a constant function will either always return 0 or always return 1, whereas a balanced function will return a 1 for half the input combinations and a 0 for the other half, so there will be 2 zeros and 2 1s in the output values of these balanced functions. In the Deutsch oracle, we are told that our black box is either a constant or a balanced function, so we can ignore any unbalanced functions. Now let's simplify things even further and just have a single input to our black box. With just one input bit, we have 4 possible functions, 2 constant and 2 balanced. One function simply sets the output bit to 0. Another function just takes the input and outputs the same value. Then there's the NOT gate, which flips the input bit. And the last function simply sets the output bit to 1. Now, computational performance is related to how many queries we need to do in order to determine if the function in the black box is constant or balanced. With classical bits, we need to do 2 queries. We need to try inputs of both 0 and 1 in order to determine if the black box function is constant or not. But with qubits instead of bits, an answer can apparently be obtained with just 1 query. Furthermore, no matter how many inputs there are to our black box, the quantum solution can be found in just 1 query. This is a type of decision problem, which is a problem that returns a yes or no result. And quantum computing is supposed to be good at solving optimization problems, because they can be implemented as repetitive calls to a decision problem. So now we need to get our heads around qubits. We can think of a qubit as being in any one of many possible states. The states and operations form a state machine on a unit circle or a unit sphere, otherwise known as a block sphere. In this example, we are only concerned with x and y values, so our state machine can be represented on a circle drawn on an xy graph. The circle has a radius of 1 and is drawn around the origin. Then the coordinates of 8 evenly spaced points around the circle forms our unit circle finite state machine. We can now think of a qubit as being a circular disk with a single dot on its circumference corresponding to one of these 8 positions. Regardless of which of these 8 states the qubit is in, when we measure it, the state is said to collapse into a classical bit value of 0 or 1. Qubit states can be shown using Dirac vector notation, which shows the value of a vector between a bar and an angle bracket. If a qubit is in a state where the y-coordinate is 0, then when measured it will produce a classical 0 binary value. And if a qubit is in a state where the y-coordinate is 1 or -1, then when measured it will produce a classic 1 binary value. The other 4 states have plus or minus 1 over the square root of 2 as their x and y coordinates, and these are called superposition states. And there is an equal probability that these states will collapse to a 0 or a 1 when measured. It is also useful to know that we can initialize a qubit to a known state, and we can use quantum logic gates to perform operations on qubits. And one of these quantum logic gates is called the Hadamard gate. If we only consider x and y values, then this gate effectively rotates our circular disk around a line that goes through the origin at an angle of 67.5 degrees from vertical. So the state of the qubit will flip to the opposite state around this 67.5 degrees axis. In quantum circuit notation, this gate is represented by a capital H in a box. This gate can be thought of as operating on the block sphere. But we're not going to consider states on the block sphere because it's much more involved and it's not required for this example. The Hadamard gate is said to put a qubit into superposition. Another two gates that we need to know about are the NOT gate and the controlled NOT gate. The Pauli X gate is the quantum equivalent of the NOT gate used in classical computing. It effectively flips to the opposite state on our unit circle around a line that's 45 degrees right of vertical. And in quantum circuit notation it is represented by an X in a box. The controlled NOT gate does the same operation, but only if another qubit called the control qubit is at a state of 1. So now we'll consider the quantum black box circuit with just one input and one output. Like the classical case, there are 4 possible operations. Unlike the classical case, in quantum computing, the functions should be reversible. So if we apply a constant function, such as set the output qubit to 0, then it would be nice to be able to apply a function called reverse constant 0 that would set its output qubit to be the same as the original input. But we can't do that if the original input is lost. Problem is solved by including an extra qubit that will be used to form the output, thus preserving the input qubit. As a result, we have 2 qubits going into the black box and 2 coming out. Then, using these 2 lines, we can construct the quantum circuit notation for the 4 possible functions, which are: set the qubit to 0, set the qubit to 1, do nothing to the qubit, and flip the qubit. And so one of these is inside the black box. By applying some NOT gates and some Hadamard gates, we can produce a circuit whereby the output qubit will be 1 if the black box contains a constant function and 0 if it contains a variable function. But in this example, everything is 100% deterministic. And so there is no reason why we can't model or simulate this with classical computing using 3 bits to represent the 8 possible qubit states. Then the classical solution would have the same order of complexity as the quantum approach, making it equally as good. Not only that, but the quantum system will require several executions due to errors, whereas the classical system will work first time, making the classical system the easy winner. But what about the performance of algorithms that claim to make use of entanglement? Take Shor's algorithm, for example, which is used for integer factorization. It is supposed to run in polynomial time, which means it should be fast, unless the error correction takes exponential time, which could make it slow and no better or possibly worse than a classical computer. The promised superiority of quantum computing remains unproven. If they could operate without succumbing to errors, then Shor's algorithm would be able to break the normal type of encryption used on the internet. But no existing hardware platform has been able to provide the error correction required for large-scale quantum computation. And if the error correction increases exponentially with the number of qubits, then the perceived advantages of Shor's algorithm will be unachievable. If superposition and entanglement were really happening, then we would struggle to simulate a quantum computer on a classical computer. This is because to simulate n entangled qubits, we would need 2 to the power n bits of memory in order to represent all possible combinations of the combined states. But so far, quantum computers have not been able to deliver the promised superfast times. It has been proposed that the error correction issue cannot be solved, making it impossible to demonstrate quantum supremacy. It has also been suggested that the existing noisy outcomes should be relatively easy to simulate on a classical computer. As the number of entangled qubits increases, the errors or noise increases exponentially, which is what we might expect if the errors were not errors at all, but were an inevitable part of a classical physics explanation. And so for a disbeliever, the evidence from quantum computing would appear to favour the viewpoint that superposition and spooky quantum entanglement are not really happening at all. If you believe in the mathematics of infinity, how should you deal with disbelievers? If we were to speak the mind of many mathematicians, it might go something like this. We don't mind being asked about 0.9 recurring by those willing to learn by accepting what we tell them. But we do mind the annoying people that simply won't be told. They don't understand convergence. They can't conceive of a countable infinite set, never mind an uncountable one. And they can't get their heads around the basics of real analysis. Then in all their ignorance, they have the audacity to insist that we're wrong and they are right. These people always think that 0.9 recurring relates to a process. Just because by their logic it can't equal a fixed value. It doesn't matter how many times we explain to them that 0.9 recurring is defined as the limit of the sequence, and that we decide on the definitions and we decide on what we accept as valid logic, not them. They still think that they are correct and all the experts are wrong. It seems like they always want 0.9 recurring to have a real world meaning. We are not saying that 0.9 recurring can physically exist with infinitely many digits. It's merely a symbol that represents the limit of a sequence, that in turn relates to a real number, which is a concept that can be defined as an equivalence class of Cauchy sequences. This means it's the abstract structure of an infinite set, containing infinitely many different but equivalent sequences, each of which contains infinitely many terms. But they think a number should have a tangible meaning that can relate to the real world and which doesn't use the concept of infinity. We can explain to them why infinity is useful, but they won't listen to us. We can give them examples of really abstract mathematics that turns out to be useful in the real world, but they'll complain that maths should not be so mysterious. We can tell them that mathematics with infinity is elegant, beautiful, and liberating, but they still think maths should be a boring mechanical way of modelling finite real-world physics. They can't even accept that infinitely many natural numbers exist, because they think numbers are in brains, just like numbers are in computers, so only a finite amount of them can exist at any one time. We can explain that mathematics is abstract and nothing to do with physical reality, but they think that sounds spooky. They might witter on about pi and the square root of 2 relating to algorithms as opposed to being constant values. But we'll assume their rejection of these constants means that we would no longer be able to use them to solve real-world problems. Yes, some maths can map to the real world, but it's still completely abstract and it can produce structures that have no physical counterpart. This is so obvious to us, and yet the disbelievers just can't accept it. No matter how clearly we explain why they are wrong, some disbelievers just refuse to listen. These people need to be told how foolish they sound. It might not be very nice, but they need to be told for their own good. Their arrogance is astonishing. They think they know better than people with maths degrees, when the simple truth is they don't even understand what a real number is. Many of these deluded idiots even think they know better than quantum physicists. It beggars belief how delusional these people can really be. Sometimes you have to be cruel to be kind. If they haven't taken an advanced mathematics course, then their opinions are worthless. They are just embarrassing themselves with their ignorance and their arrogance. It sounds like they are saying we should throw away all mathematics that's ever used infinity. It's pathetic. Not only do they think it's clever to come up with the idea that we shouldn't use infinity in mathematics, but they are so delusional that they think we're all going to say, "Oh yeah, you're right, all our work in mathematics has been a waste of time." That's how idiotic these people are. But even after being told how stupid they sound, they just carry on regurgitating the same old argument. So in the end, we have to make fun of them and tell them to go away. It's the only way to get rid of these crackpots. Once they know you think of them as being a joke, they'll go away and not bother you again. Then once they are silenced, sanity will be restored. We can then rest safe in the knowledge that we can conceive of the infinite. Mathematics is the language of the universe. It is discovered. And it can describe things that are otherwise beyond human comprehension. Once again, everything will make sense, and we can rest assured that it is an undeniable fact that 0.9 recurring does equal 1. This video is brought to you by extremefinitism.com.